Hi, everyone, and welcome to another day of science. And today, what we want to do is talk about controlling chemical reactions, particularly the speed of them. So, really quick, first, there is this question of the day. What's the difference between a chemical formula and a chemical equation? And the answer that you want to have in there is, well, a chemical formula, that's what we were talking about in the second chemistry chapter, right? For this one, we were talking about things like H2O, right? That's our famous example we've been using, a water molecule right there. So it's just, a couple atoms coming together to form, well, one particular molecule of something. Whereas an equation, that's what we've been doing in the third chemistry chapter. They're kind of like short little stories. There's a before, right? Whatever happens before, things are combining together, or things are going to break apart or stuff like that. There is the during, that's the yield sign. That's kind of like when the actual chemical reaction is happening. And then there's the after, right? And that's what is being formed or what's been, broken apart or something like that, right? So that's the difference, right? A formula is just one particular molecule, whereas an equation is kind of like a short little story. Okay, so what we want to do first is talk about speeding up chemical reactions. Sometimes, if you're a scientist, you might want to speed up how fast a chemical reaction is happening. Let's use the rubber ducky example right here. Okay, let's say you own your very own rubber ducky company. Yes, I don't know why you own your own rubber ducky company, but you happen to. Now, rubber duckies, it turns out, are in high demand. I mean, they're just, they're always selling out constantly. In fact, Amazon Prime is calling you up saying, we need more rubber duckies. And you're thinking, well, this is a problem. It's a good problem, but it's a problem because you're thinking, I own the factory that makes the rubber duckies, right? We're working everybody first, second, and third shift. So 24 hours a day, you're pumping out as many rubber duckies as your company possibly can and everything. So what do? Well, really, you're faced with two choices right here. The first one, well, it's a pretty big gamble, right? I mean, it would be, what if we build a second rubber ducky factory, right? Maybe, we add on to our factory or build another building or something like that. But first of all, that could cost you millions of dollars. Second of all, it's going to take months, if not a year or so, to get the second rubber ducky factory, running. And Amazon Prime, I mean, those people want their rubber duckies pretty quick here and everything, right? So your other option, your second option is maybe you hire a scientist, right? And the scientist might look at your rubber ducky process and everything and say, hey, I know what we can do, right? Well, the way the process is you have a little bit of the rubber, basically. They squirt it into the mold, and then the mold forms the rubber ducky, and then let's say 30 seconds later, pops out one rubber ducky, right? And you have a whole bunch of these machines doing this all day long, 24/7. But the scientist might say, what if we mix a little bit of what's called a catalyst in there, right? And the catalyst can speed up that chemical reaction. So instead of 30 seconds to form the rubber ducky, what if it only takes 15 now, right? And the good news is it's only going to add, let's say, like maybe 2 or 3 cents per rubber ducky into the formula that it makes to make that rubber ducky. But the good news is it can literally double how many rubber duckies your factory can make almost instantly, right? So that seems like the best option, right? And so all that a catalyst is in this example, it's just something that speeds up a chemical reaction. Another example could be what's called a catalytic converter, right? These are in every single car sold in the United States that is a gas running car, right? And you can see it, right? If you look like, imagine like this is the tailpipe of your car. If like you kind of like look under the car a little bit and follow that tailpipe, because that's going to go all the way to where the engine is. It's where the smoke from the engine's coming out. But in the middle somewhere, usually towards the back of the car, you're going to see kind of like a big bulge like this guy right here, and that is the catalytic converter. Now, here's the thing, right? When your car makes explosions, right, because that's what's making the car go is little tiny mini explosions inside the engine. That's what's pushing it forward. It makes carbon monoxide, right? And carbon monoxide, it's not good for you. I mean, it's really bad. It can kill you really easily and everything. In fact, really older cars, that was a problem, right? If you walked behind the car and it was running and you breathed too much, yeah, you could just keel over and die, right? And so modern cars, when they make them, because you have the smoke coming out, they decide that's not going to be a really good thing and everything. So what they do is they have basically this honeycomb of stuff that the smoke goes through, and it makes a chemical reaction happen much faster, right? And what happens is the carbon monoxide combines with all the other elements that are in there, and it forms carbon dioxide, right? Which is this guy right here, carbon dioxide in water, right? And so that's why a lot of times if you see a tailpipe and some water's dripping out of it, it's a chemical reaction because of that catalytic converter. It's just they're literally trying to keep you alive and everything. So like older cars used to have that problem, whereas modern cars, I mean, it's not good. And if you just breathe just that stuff, it'll still still kill you. But at least it's not like you walk behind the car and you just keel over dead. That'd be bad and everything. Okay, that's not the only thing that we have that speeds up chemical reactions. Enzymes also do the same thing, but they're more of, instead of being like something that scientists created, they're just a natural enzyme that happens. Right? So enzymes, right? They speed up chemical reactions. And again, us eating is a whole big chemical reaction going on right there. It's actually a whole bunch of chemical reactions happening. And without enzymes, well, we wouldn't be able to digest our food fast enough. We'd still be starving to death. Even though you could like fill your belly with food, you wouldn't be breaking down the food fast enough to get enough energy to survive, right? And so we're constantly digesting food. In fact, when do you start digesting food, right? Let's say you go and you eat something, say like, there's a pencil here. You're starting to eat the pencil. Well, hopefully you have better food than that. But you know what I mean? If you put it in there, when do you start digesting your food? The moment you put it in your mouth, right? In fact, you start digesting it the second it goes in your mouth. You do two things to start digesting your food, right? Now, the first thing is you break it up with your teeth, right? Your big chopper is right there. That's part of digestion. It's increasing the surface area of the food so that basically then you can digest it faster. And the moment it gets wet because of the saliva in your mouth, in your saliva, there's an enzyme called maltase, right? And the maltase starts digesting the food. Gross, you say, right? But that's just part of digestion right there. So the moment food goes in your mouth, you're literally starting to digest it right away. You don't believe me? Well, try this, right? You can do this at home. Let's say you have some kind of just plain cracker, right? So it's just some kind of salty cracker and everything like that. In order for this kind of mini experiment you could do at home to work, it can't be a sweet cracker, right? It can't have any kind of sweet stuff on it. So what you do, you take the cracker as big as you want, right, that you can fit into your mouth and everything. And what you do is you take the cracker, put it on your tongue, so just kind of lay it on your tongue right there and everything. And then the hard part of this mini experiment is you have to resist the urge to chew it or do anything with it. What you want to do is just kind of leave it on your tongue and just let saliva go on the thing, which is kind of gross and everything, right? Leave it there for 1 minute, 2 minutes, 3 minutes, maybe even more. But eventually what's going to happen is it's going to start to digest right there in your mouth. And if you leave it there for a couple minutes, basically the maltase here is going to start breaking down the, some of the fibers that are inside of that cracker. And they're literally going to start digesting it. And it's going to turn the starch that's in there into sugar. And so you can actually, if you wait a couple minutes and then, you start thinking about it and tasting it, it literally gets really sweet, right? Because it's turning into sugar right there in your mouth. It's literally starting to digest for you right there, which, it's kind of gross to think about and everything, right? Okay, let's see. You're moving on. Oh, and then that process continues on. You have other enzymes, trypsin and lipase, that as, basically the food goes down through your esophagus and into your stomach and large intestines and small intestines and everything. There are different enzymes in there to break down different parts of the food that you're eating and everything. Same thing, just so you can digest it and everything. Oh, yes, and that brings us to the joke of the day, right? If I were a DJ, I'd be named DJ Enzyme because of what? We're breaking it down. Get it? Enzyme? Breaking it down. Never mind, moving on. Okay, sometimes you want to do the exact opposite, right? Instead of getting that chemical reaction speeded up, some chemical reactions we definitely want to slow down, like this guy going on right here. I mean, no one wants bread that looks like that, because okay, that's disturbing. Let's move on here. So sometimes what the scientists do is they'll include what's called an inhibitor, right? And this is a material that slows down a chemical reaction because sometimes you don't want it going quite so fast and everything. So let's say for bread, for example, right? If you make fresh baked bread at home, right, you only have a couple days to eat the thing before it, goes back to that, before it looks like this and everything. Oh, that's terrible, right? So you got to think about it. If you go to the store and you buy a loaf of bread like this, now think, it was made in a factory somewhere, right? By the time it can actually go and leave the factory is at least a day or two, right? Then it might take another 2 or 3 days to ship to get to the store. It gets to the store. It might sit there for a week or more, before you buy it. You bring that fresh loaf of bread home, and then it might sit on, in your, kitchen for like a week or so before you finally get to like the last slice of it. So think about it. I mean, that bread, it's at least, when you're eating that last slice, at least 2, maybe even more weeks old and everything. So how do they keep it from looking like, oh, like that? Because that's what would happen if it was your bread at home, right? Well, what they do is when you look at all those ingredients and you see all those really long words that no one can pronounce and everything, some of those are inhibitors and they're just keeping it from looking really terrible. And in fact, this is really common. I mean, think about it. Last time you bought your favorite bag of chips, when was the last time you opened the bag up and, freshly opening it for the first time and you're like, I hope that this bag is fresh. I hope it's not like the last one and all terrible, right? Well, again, that doesn't happen because of inhibitors that are in there. I mean, medicine, same thing, inhibitors, right? Well, we don't even need to go into like, kind of those little snacky things and everything like that. But yeah, inhibitors are causing, basically, they're causing the chemical reactions to happen much, much slower. So, well, that doesn't happen, or this doesn't happen. Oh my goodness, that's just not good if that's your food. I mean, okay, we don't want to think about that. All right, let me show you a short little video talking about some of this stuff with speeding up and slowing down chemical reactions.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has some more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
All right. Hey, the last thing, we've already actually talked about this one, surface area. If you want to speed up a chemical reaction, kind of like they were talking about in that funny little video, you increase the surface area. That's where they were talking about breaking up the groups of kids and everything. And we talked about this one with digesting the food in your mouth, if you remember, right? When you break up a cracker, you increase the surface area as the example, and then that, makes the saliva touch more of the cracker faster and it can digest faster. Or a bed of nails could be another example, right? If you lay down on one nail, well, that's going to hurt a lot, right? But if you've got a whole bed of nails, a whole bunch of nails that you lay down on, well, that increases the surface area, and so it's not nearly as bad because of that. Hey, really quick, normally we do this worksheet together, but I'll just go over it really quick with you together, right? A couple ways that you can speed up chemical reactions. So here's a couple of them we just talked about. Well, obviously, increase the surface area, we were just saying, right? You could add heat. The molecules will be moving faster to bump into each other a little bit faster. Enzymes, remember, a chemical that speeds up the chemical reaction. Or a catalyst, right? A catalyst will also speed up those chemical reactions. The enzyme actually just is a natural catalyst. Okay, activation energy, right? This is the minimum amount of energy you need to start any chemical reaction at all, right? In fact, it turns out there's always going to be, in every chemical reaction, there's always some kind of change in energy that's going on because of that and everything, right? And so every chemical reaction, if you remember, I gave you the example earlier about little frogs trying to jump over the wall. They need to have a certain amount of energy to get over that wall, which is to start the chemical reaction. Let's see for this one. 3 things that you need to start a fire. Again, we talked about this one too, right? You need fuel and oxygen, but you also need a certain amount of heat to get that fire going and keep it going and everything. What about a chemical reaction that appears like it doesn't need any kind of activation energy, right? You just mix the 2 things together and instantly it happens. Let's say vinegar and baking soda. When you mix those together, the chemical reaction happens without any activation energy. Well, it turns out the energy that it needs is very, very small, and it's just absorbed from the temperature that's in the room or around it right there. Chemical reactions that have so much energy that they're giving off energy are known as exothermic. So think like fire burning. It's got so much energy that it just gives off heat. Whereas some chemical reactions are called endothermic, right? This is the one, remember the chemical reaction in a baggie, or those little bags that like get ice, if you get sprained ankle or something like that in a first aid kit and you gotta smack them. That's an endothermic reaction. There's so little energy, it's actually pulling energy from around it, and that's why it feels really cold. And then the last one, the law of conservation of mass, right? Well, that's going to be this first one, right? The mass of the reactants must equal the mass of the products, right? You cannot create or destroy matter with chemical reactions. Okay, hopefully all of this helps you, and remember to take the quiz at the end.